Happy birthday, Shankar. It's almost a job requirement to be an academic to have ADD, a form of attention deficit disorder. So I can see, for example, Mike is checking email. Sorry, I didn't mean to point on you. But I think Shankar is even better because not only he can do that, but he can sleep while it's happening, and he can also send you an email while he's asleep. In the same meeting, you have to ask Stephanie how that happens. So in order for all of us to collectively reach such a level of mastery of this multitasking, I thought I'd give 2 talks at the same time. One about Shankar and one about some research. So starting with a historical perspective, and it's nice because we have all the protagonists in the room. Praveen is here, Roberto, and many others. And looking at the archives, we have a library at ITS, so it's easy. We just ask the librarians to pull the reports. I went back to the old architecture of the AHS system, and I think this is really a homework for half a century, and that's the point of my talk today. So starting with the very early ages of the automated highway system and the platoons that Shankar's team did with many others here, if you look at automated driving, there's already 4 generations. This is Richard's vehicle, I believe. Then the Google vehicle, which can pretty much do the same job in a somewhat unsupervised environment up to 25 miles an hour. And the next generation, which used machine learning to basically plug in yourself inside your autopilot after learning how you drove before the software upgrade. And this is probably 10% of the job, and here's why. So first, and this is, I also went to look at the old movies. This is the original 1997 demo. You probably recognize it. There's a huge legacy at Berkeley following Shankar's work, which has perdured almost for 20 years. We've been running, not so lately, automated snowplows. You can imagine how difficult it is to have an automated vehicle go in the snow. And some of the teams at Path nowadays are running automated bus lines in Eugene, Oregon. So promising to deliver on my ADD comment earlier, I'm going to keep showing you a couple pictures of Shankar to show Shankar throughout the history of this. This is roughly around 2010, so the snowplow time, and this is a picture of Samuel when Samuel was younger. But so now going back to the other talk, so why is green future with automated driving not so obvious? This is the statistics we're working on with the DOE. And you think about automated driving is not necessarily good. For example, if you have an automated car, it's likely that you could potentially go 80 miles an hour on the freeways in the near future, which would be really disastrous for energy consumption. But if you do it with platooning and you combine the two, it's actually good. So the future of automated driving ranges between a 90% energy reduction due to mobility to a 200% worsening. And we don't know where we're going to be. And this is where the work of smart cities start. People think about smart cities nowadays, and it's a very catchy buzzword. And so when you ask planners, this is what they show you. That's the vision of a planner. And what I like to do is explain why this is a 50 years homework that Shankar started 20 years ago. So this is a vision of what's happening in San Francisco today. So you have bikes between cars, so basically bikes being run over by cars because there's no bike lane. You have vehicles that are nearly empty, stuck in traffic with, and the color coding denotes specific vehicles. For example, the buses are in yellow. The parkings are full. It's a nightmare. You can't really move in the city. And the notion of a city planner is that over the next 20 years, this is going to change incrementally by first keeping the congestion level at the same level, because you don't want to empty the streets, otherwise more people come. That's latent demand. But at the same time, making it more efficient. So for example, you're going to have a lot more shared vehicles or mobility as a service vehicles like Uber and Lyft that don't need parking anymore, and therefore the parking occupancy goes down. And as you do this, you start to see some green space and potentially space for bike lanes. And as this urban evolution continues, there's more and more green space. There's also more and more parking because progressively you're reducing the number of lanes. You don't want to make it smooth. You absolutely don't want to kill congestion. You just want to make less people on the street and more multimodal until ultimately your city evolves and becomes all green. So that's why we only did 10% of the work, because if you go back to this architecture, in a sense, the regulatory layer is almost there. But how you make this work in the city is a much, much more complex process. And so going back to my other talk, so this is Shankar, nearly a civil engineer and planner. This is in Singapore when he was inspecting the Create building, and this is here in the opening. So working also at longer time scale. And now going back to this first talk, This is really the job that needs to be done. I mean, in a sense, this has been not beaten to death, but this has been quite well investigated. But how you make it work at the scale of a city, this is probably the next 30 years in urban planning and engineering. Now, this is 1997, so fast forwarding to 2005. This is kind of back to the future when this all started. When I started working on this problem, this is a picture of Shankar, so going back to Kameshwar's earlier comment, you didn't change too much. And one could argue that for planning, phase one was really the last decade. Phase one was really bringing traffic information availability to the cities. So I started working on Mobile Millennium, and Shankar was instrumental in getting my program launched back in 2006. And the achievement of Mobile Millennium, which was really a phase one thing, was to bring online traffic information that was mostly connected from smartphones, such as this one, which was the NEC Plus Ultra phone at the time, and now looks like vintage. This picture is from November 10th, 2009. I want to thank you, Shankar, because when we launched the program, it was really difficult to convince the DOTs to do it, and you came to all of the events, to the media events, and to the DOT events, and this is a very common thing we've seen with you at Berkeley is your strong support for assistant professors and young faculty to get their career started, so thank you for that. Going back to the other talk, the Mobile Millennium, as it started running, was one of the first systems that collected data from mobile units at a fairly large scale. And this, for example, here shows the data, the way it looked with 500 vehicles in San Francisco. You can imagine Uber today has 2,000 vehicles live at a given time in the city. And of course, that doesn't even count all the phones that are available. So this data has enabled information at fascinating scales. This has really brought the first revolution to transportation, which is really traffic information. So right around the time the project concluded, happy events happened in both our families. This is Samuel when he was young, and this is Miriam. And they used to play a lot together at the time. And so now going back to the other talk, this is what my job was at the time. My job was to understand how to build information from this data. This data, this is a time-space diagram. That's the common tool used by traffic operations people to display traffic information. This is time, this is location, and the color index indicates the level of congestion. So the first step is really to do estimation. We've heard a lot about estimation in this set of talks. And so basically how you, from very low sampled information, how you construct traffic information at global scale using estimation techniques. And so that, in a sense, one could argue is a very mature thing today. It's been implemented by most of the major companies that work in this field. That first phase enables the next phase. This is a nice picture from an Italy vacation back in 2010. So now that, in fact, since we're talking about Italy, I should show this, which is way more interesting than the industry logos. So that brings us into phase two. The thing is, phase two now has enabled decision support systems. What's interesting about decision support systems is that they're mostly based on infrastructure. So you could view estimation as one of the blocks, and that's work that Roberto and Praveen and I worked on together. With some demand prediction, would provide some optimal control wherever you can control traffic. Where you think you can control traffic is where there's infrastructure. For example, along the 210 corridor, these are the points where you can control it. And we know what that means is assembling all the control infrastructure that you can think of. And there is actually not much. So the job of a traffic engineer is to make this all blue or all green, because any red is congestion. And Claire asked me to be in a security session, so that's why I plugged this, which is what could go wrong in phase two. Well, what could go wrong is that a hacker could take over that infrastructure. And so as part of Forces, which is the program that Shankar put together with the NSF, part of the work we did is try to show that with specific vulnerabilities, you could almost achieve any pattern you would want in traffic. So of course, we don't do graffitis here because we respect our infrastructure. So the graffitis we do on the space diagrams, and drawing CAL logos on time-space diagrams would be this. Now, the history of this is when Shankar told me about this in 2005, we really thought he had lost it. Because at that time, we were working on mobile sensing for water with the hope of doing better water distribution. I was also trying to find a picture of Sorab where he still looks like a student, because now he's wearing ties and jackets. So hopefully I did a good job here. So this is what Shankar looked like at the time. And so Shankar told us, why don't you guys do hacking water? And we heard a lot of hacking from Richard earlier today. And so that was part of Sorab's thesis. We hacked water canal in France to show that with specific spoofing attacks, you could achieve specific perturbations in the system and infer from it how to protect it. So this is how the whole work in cybersecurity in traffic we're doing now started by this, which today, I think, and we heard from Bruno, is a very common thing to work on this. But in 2004, that was really futuristic, because nobody really thought about these problems, at least in the context of infrastructure. The title is wrong, but I still wanted to show this picture. This is Samuel's birthday. So now the thing is, in phase 2, you're trying to control the infrastructure. The problem is it's very likely that phase 2 will completely bypassed by phase 3. Why? Because the government is losing control of its infrastructure. That's because the government doesn't really manage your decisions, at least not yet, before the elections this year, and not in the US. But the notion that you could actually manage traffic is probably going to become more and more of an illusion, because what are you using to go to traffic, to go to your destination? You're using a lot of tools which are based out of your mobile phone. So we're back to this mobile phone problem. So think about a very classical problem in transportation engineering, which is the user equilibrium problem, where you're trying to understand, for people who live here and who work here, what is the main routes they're using to figure out their routing. Well, there's a lot of couple sequential decision problems in which basically, you look at Google, Apple, whatever you're using, it figures out a couple routes. You pick the one you want, and in a sense, the role of the infrastructure on this is fairly minor. So you could view Waze, Google, Apple, Inrix, Bing, or whatever app you're using as competitors, all competing for the same resource. Okay, it's a network allocation problem. And then all the Waze users will be allocated to specific routes with specific proportions, and the user using another app will be on the same routes with other proportions. There's no model for it. There is something called the user equilibrium. It doesn't cover this scenario. And so this scenario is becoming more and more important, and that's the things we do in forces, because basically first, few people use apps, but as more and more people use apps and are very excited because these apps are supposed to decrease traffic, actually the opposite happens. They start to congest secondary streets until people get really unhappy and potentially sabotage them by sending some of their senior citizens of their community walk along the street pretending their car stuck in traffic so that the app figures out they shouldn't drive through their neighborhoods. And it gets to the political level. And of course, we all know that despite all these ads in the newspapers, a Nash equilibrium, which is essentially what it is not optimum. And so that's the type of work that Shankar has enabled as part of our forces. And it is very important, because this is going to be the way mobility is managed at global scale in the next decades. This is unrelated to the talk, but since we also met in Singapore, I thought I'd show this picture here. So there is, going back to this talk, I think then we will be done. There is mathematical models that can be derived for it. I think if I didn't show an equation in this crowd, I would be crucified and not being taken very seriously by some. So I'm going to show some equations, even though obviously in 13 seconds there's no time to go through them, but at least I've done. And I'll show one theorem too, because otherwise it's not fun. I guess my point here is that what happens in the classical one population case, where you have a very nice convex program solving a user equilibrium, which is a Nash formulation, it doesn't generalize as well in the multi-flow case. And in that case, in a sense, even though the problem is not convex, you can solve it by block coordinate descent, which in a sense identifies an equilibrium, which solves a Nash problem, which is a generalized Nash problem, but not as a convex program. And that's the best that can be done to solve these problems today. So finishing the talk, these things are real. There's going to be policy that comes from it. And just to show you one last numerical example, imagine if overnight, 15% of the population started to use a single app. Okay, so that app would route them through that corridor, and they would choose to, exit the freeway and use nearby streets. Computing the impact of such decisions on travel time is essential, because in a sense, what it will lead to is a negotiation between the cities and the state on who should pay for that. What happens in the process is, of course, people leave the freeway. So as more and more people leave the freeway, well, travel times decreases on the freeway, and the things get worse and worse in the city. That's right around Richards Alley in Pasadena, until basically a Nash equilibrium is reached because there's no incentive to change. And solving these problems is not obvious when you have multi-commodity and when you only have partial model adherence. And that's the interesting work we want to do. You can plug on top of it a security layer if you imagine that the users are spoofed. As we've seen before, that happens quite often. That's called demand management. As the dean, a lot of demands come your way, and so you have to manage them as well. This was one of them by George Lightman for his Legion of Honor. I want to really thank you, Shankar, for all the leadership you've put in this university, both as a researcher and also as a wonderful dean and colleague. And again, happy birthday. Thank you.